Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you all to the class of reanalysis. In today's lecture, we are going to discuss the fourth method to show that Q is not a complete ordered field. Uh, so far, I have discussed three methods in my couple of lectures that Q is not a complete ordered field. So, to show what strategy we will use to show Q is not a complete ordered field, we will assume here a subset of Q, a non-empty subset of Q that is bounded above but has a now rational supremum. That is, the supremum of set S does not belong to Q. In that case, we will say Q is not a complete ordered field. So to show that Q is not a complete ordered field, it is sufficient to show that there is a subset of Q which is bounded above but has a no supremum in Q. Actually, this is called the supremum property or least upper bound property. If a certain field does not satisfy this least upper bound property, then we say that that field is not a complete ordered field. So for this, I am going to assume a rational subset, subset of a rational that consists on all those positive rationals whose square is less than 2. This is my subset S, which is a subset of a rational number, set of rational number Q. Firstly, to prove properly, I want to discuss some things that are very important here. What type of the numbers are in set S here? The first important thing, what types of numbers are in the set S? You can observe that the set S consists of all those positive rational numbers whose square is less than 2. If you solve this inequality, x square less than 2, x square less than 2, by taking square root on both sides to find x, we have, this implies x is less than square root 2. But our x is positive, so x in this case lies belong to the open interval 0 to square root 2. So our set S in simple words equal to all those rational numbers that lies between this interval. Suppose this is our rational line Q, this is our set S, this is our set S, this is our set S. Now now the elements of set S lies between this interval. Now elements outside this interval that are here shows the upper bounds of set S. So all the elements to the right side of square root 2 shows the upper bounds of set S. You know, upper bound is an element that is greater than every element of set S. So all the elements which are on the right side of square root 2 are greater than the elements of set S. Next important thing, I want to ask if y is a certain element of set S, y is a certain element of S, and suppose k is the supremum of set S. If y is an element of set S and k is supremum of set S, I want to ask, is it possible in this case that y is greater than k? Is it possible that y is greater than k when y is element of set S? This is not possible, because if y is an element of set S, then y should be less than or equal to supremum of set S. It cannot be greater than the supremum of set S. The third, if y is an upper bound of set S, now is it possible that y is less than the supremum of set S? This is not possible. This is not possible. And also, this is not possible. So these are the two main concepts that I will use in proof of uh, proof of the theorem of our problem. So we start. We can notice that one is an element of the set S, because the set S, otherwise you can see that there are infinite elements in the set S, and S set S in this case is non-empty. But there is no need to elaborate all of these in this proof. You can simply write it as one belong to set S, because this set consists on all those rational numbers which are positive, and whose square is less than 2. So 1 is an element of set S, because 1 is greater than 0 and square of 1 is less than 2. So clearly 1 belongs to set S. This shows that S is non-empty. Next, clearly 2 is an upper bound of set S. You can notice that there are infinite elements which are the upper bound of set S. So 2 is one of the element here in this region that will be upper bound of set S. So clearly 2 is an upper bound, 2.5 is an upper bound. Every element that is greater than square root 2 is an upper bound of set S. Every element that should be rational. So clearly 2 is an upper bound of S. It means S is non-empty. S has an upper bound. This shows that S is non-empty bounded above subset of a rational number Q. Therefore, S is bounded above. Thus, S is a non-empty set of rational numbers and bounded above. Next now we will show that this set S has a no rational supremum. Let, if possible, the rational number K be its least upper bound. So now we suppose that the set S has a rational supremum K is here supremum of S, and it is a rational number, if possible. Be its least upper bound, or you can say this is the supremum. Clearly K is positive. Why K is positive here? Because your set S consists on all positive rational numbers. So it is clear that if a set is a set of positive rational numbers, then its all upper bound will be positive. As you can see here, this is our set S that consists on 0 to square root 2 open interval. So all the numbers that are greater than square root 2 on the right side are all positive. So if K is supremum of the set S, then clearly K will be positive here. Next, I will use trichotomy property. Trichotomy property also hold in rational numbers. Trichotomy property says that if A and B are any two elements, then either one of the possibility hold. Either A is equal to B, either A is greater than B, or either A is less than B. So here I will use trichotomy property for two numbers. One is K square and other is 2. So one of the possibility will be hold here. Either K square is less than 2, either K square is equal to 2, and either K square is greater than 2. Why I am comparing the K square with 2? Because here I have in our set S, we have choose all the elements whose square is less than 2. So that's why I am comparing K square with 2. Suppose I choose a set S such that whose square is less than 5. Whose square is less than 5. Then I will compare K square with 5 simply. So trichotomy property says that either one of these three cases hold. So in case number 1, when K square is less than 2. Now this is important. I want to prove this case is not valid. This is a wrong case. All of the three cases are wrong. This is my target. How I will prove that this case is wrong? I will use the concept of this. I will choose a rational number Y that will be element of set S. Further, I will show that Y, which is actually this element of set S, and it is greater than k means supremum of set S. That leads to the contradiction. So let us consider the positive rational number that will work here. 4 plus 3k over 3 plus 2k. Can you choose any other rational number? Yes, you can choose. There are many other rational numbers you can choose here. Suppose you can try to take y is equal to k plus 1 by 2 and comments me whether this y is equal to k plus 1 by 2 work here or not. Let y is equal to 4 plus 3k over 3 plus 2k. This y is clearly positive and rational because k is positive, k is supremum of set S and the supremum of set S is clearly positive. So numerator and denominator both are positive. This implies y is positive. So the first condition for the set for an element of set S is fulfilled here, that all the elements of set S should be positive. So y is positive here. Next I will show that if y belong to set S, it should be satisfied the following condition. Y should be positive, y square less than 2, and y should be rational. It is clear that y is rational. It is also clear that y is positive. Next I will show that y square is less than 2. And lastly to prove this case is not valid, I will show that y is greater than k. Y is greater than k. Y is greater than k is actually not the condition, not the required condition that y is an element of set S. For y is an element of set S, there are the only three conditions. Y should be positive, that is clear. Y belong to Q, that is also clear. There is only third condition remaining, y square should be less than 2. That we will prove after this. Firstly, to show that y is greater than k, mean to say y is an element of set S and y is greater than k, supremum of S, I find the difference k minus y. Y is here 4 plus 3k over 3 plus 2k. By taking LCM here, we have 2 into k square minus 2 over 3 plus 2k. Here in this case, because case number 1, our k square is less than 2, this implies k square minus 2 will be less than 0. So the numerator is negative and denominator is positive. Final fraction negative over positive will be less than 0. This shows that k minus y is less than 0 implies k is less than y. Say this as inequality number 1. Next I prove y square less than 2. So for this I calculate 2 minus y square and show that 2 minus y square is greater than 0. When y square is less than 2, it means y square minus 2 is less than 0 or 2 minus y square is greater than 0. So just a minute, Azan has been started. Okay, next we calculate 2 minus y square. 2 minus y is 2, 4 plus 3k plus 3 plus 2k whole square. By taking the LCM and after some calculation, we have 2 minus k square over 3 plus 2k square. In the numerator, 2 minus k square, as k square is less than 2, so 0 is less than 2 minus k square. In other words, 2 minus k square is positive. So the numerator is positive and the denominator is a perfect square. So the final fraction is positive. This shows that 2 minus y square is positive, or in other words, y square is less than 2. Now, y square less than 2, y is positive, y is assumed as a rational number. So these things shows that y is an element of set S. And from the inequality number 1, that was y is greater than k. So this leads to the contradiction of our assumption that k is the supremum of the set S, because here y that is the element of set S. Now it is greater than the supremum of k. This is not possible. From 1 and 2, we have y belong to S, thus the member y of S is greater than k, so that k cannot be an upper bound of S, and hence this case is not valid. So the in the first case, when k square is less than 2, then we show that this case is not valid. Now we move towards the second case. In the second case, when k square is equal to 2, if you solve this equation k square equal to 2 and k is here positive number, uh, you have only one possibility. By taking square root on both sides, we will get k is equal to plus minus square root 2, but k is positive here. So there is only one possibility, k is equal to square root 2. Square root 2, you know, this is an irrational number. So this case is not possible clearly. What we will write for this case? We have already shown that there exists no rational number whose, where we have shown in my first lecture, I have proved that square root 2 is an irrational number, or in other words, we say that there is a no rational number whose square is 2. Can you find any rational number whose square is 2? This is not possible. There is only one number whose square is equal to 2, that is square root 2, but square root 2 is not an irrational number. So this case is not possible here. Thus this case is not possible. Now we move towards the third case, when k square is greater than 2. To prove contradiction in this case also, we will use the same strategy that I have used in the case number 1. Again, considering the positive rational number y as defined in case number 1, we will choose the same rational number y, that is equal to 4 plus 3k over 3 plus 2k, and I will again calculate the difference y minus k and the difference y square minus 2 or 2 minus y square. Again, by using the steps that we have used in case number 1, but now in this case our k square is greater than 2. When k square is greater than 2, it means k square minus 2 will be greater than 0. So by using this concept k square minus 2 and by calculating the steps of case number 1, we can deduce from inequality number 1 and 2 respectively. Now y is less than k and y square is greater than 2. What does this show that? This shows that hence there exists an upper bound y of s smaller than the least upper bound k. This is right that upper bound always greater than least upper bound. This is true, always true. But how can I say that y is an upper bound of the set S? How can we say that y is an upper bound? This is true that upper bound is always greater than least upper bound. So least upper bound, in other words, least upper bound should be less than upper bound. But how can I say that y is an upper bound? If you notice on this condition, y square is greater than 2, what does this show? When y square is greater than 2, if we taking square root on both sides, we have y is greater than 2. This shows that all the rational numbers which are greater than square root 2, mean to say y greater than square root 2 lies in this portion. Y is greater than square root 2, and this region shows the upper bound of set S. If you solve y square greater than 2, this gives us y greater than square root 2, and y greater than square root 2 lies in this region that shows the upper bound of set S. That's why y is here upper bound of set S. Now, if y is an upper bound of set S, is it possible that upper bound should be less than least upper bound? Upper bound, is it possible that upper bound is less than least upper bound? Because k is our least upper bound. This is not possible. This is not possible that upper bound is less than least upper bound. That leads to the contradiction of our assumption. Hence, there exists an upper bound y of s smaller than the least upper bound k, which is contradiction. Thus, none of the three possible cases hold. Hence, our supposition that a rational number k is the least upper bound of S is wrong. Thus, no rational number exists which can be the least upper bound of S. Hence, Q is not a complete ordered field. If here we choose our set S as a subset of the real number, set of real number R, and K, that is the supremum of set S, is an element of set of real number R, then this is true. Then in that case, this set will be the supremum of set that will be belong to the real field. But in case of Q, all of the three cases cannot be held. Hence, Q is not complete order field. I hope today's lecture is helpful for you, and now you have a clear understanding of all of these concepts. But if you find any deficiency or any want to ask any question, you can comments me. Inshallah, I will reply you. So, inshallah, we will meet in the next lecture. Until then, take care. Allah Hafiz.